Hello, this is Tyler Beamer. This is instructional video for Math 130, College Algebra. Uh, this video is in regards to Chapter 6, Section 3, Exponential Functions. I am working off of the notes that are on Blackboard, so you can pull those up and kind of follow along if you'd like. So the first part of this particular section does a quick review of the laws of exponents. We've already talked about this in the chapter R that we did at the beginning of the semester. I'll just review them real quickly. So if you're multiplying expressions that have the same base, we can keep that base, add the exponents. So for example, if you were going to multiply x to the third times x to the fifth, that would be x to the eighth. Okay. This is using the power to power rule. So if you're taking an exponent, raising that to another exponent, keep the base, multiply the exponents. So for example, if you had x to the second raised to the third, that would be equivalent to x to the sixth. And then this is also pretty much using power to power as well. It's assumed that both of these bases have an exponent of 1. And so when you multiply each of those exponents of 1 times the exponent that it's being raised to, you essentially get that exponent that it's being raised to. So a to the s times b to the s. I can zoom in a little bit here. Oh, that was a little too much. If we're raising a base of 1 to any exponent, that's going to equal positive 1. You can make negative exponents positive by moving them to the denominator. And anything to the 0 power is equal to 1. So we've already talked about these in the chapter R, but this section does a quick review. Alright, so on to the main agenda item, which is exponential functions. So exponential functions have this form where we have some constant c times some base raised to the power of x, where a, this base, is a positive real number, and this constant c cannot be equal to 0. The base a is what we call the growth factor, and then c would be the initial value. So the base c essentially tells the function how quickly it's going to be growing. The larger that base a is, the faster the exponential function will grow. And the smaller it is, the less quickly it will grow. Okay. If we're looking at exponential functions that are growing, so exponential growth and not decay, the graph would look something similar to this. So here's an example of an exponential growth function. So you can see that this is definitely not linear because you have this curved aspect to it. One of the main characteristics of exponential growth is that you hit a certain point here, then an inflection point where the growth really starts to take off, and you really start to get that curved aspect of it. Exponential functions are great for modeling applications where things are increasing rapidly. So population size is something that typically grows exponentially. That's one application that's used quite often, and we'll look at an application of that. Okay. All right. So some properties of an exponential function where a is greater than 1. Okay. So if we have a greater than 1, then we should have exponential growth. The domain is going to be negative infinity to positive infinity. Okay. There's no x-intercepts, so the graph actually won't intercept the x-axis. The y-intercept is 1. This talks about horizontal asymptotes, which we hadn't really discussed a whole lot, so you can kind of ignore that. Um, and it is an increasing function like we just saw and is 1 to 1. So it passes the horizontal line test. So let's take a look at a quick application of an exponential function here. Let me zoom out so where you guys can see this entire problem. I apologize with the zooming part here. Okay. Alright, so India is currently one of the fastest growing countries. By 2040, the population of India will be larger than the population of China. By 2050, nearly 1/3 of the world population will live in these two countries alone. The exponential function 574 times 1.026, so where this is the growth value, since this number is greater than 1, right, we're going to have exponential growth. Okay, so that's positive, greater than 1. So basically that tells you that the growth factor is going to describe exponential growth. So that models the population of India in millions, X years after 1974. So the first thing says to graph the function. And so we could graph that on our calculator here. So if we go to y equals, so 574, 1.026, and then to do an exponent you're using the caret button, so that's right below clear. So to the x, and you can definitely see that curved aspect. That certainly looks like exponential growth. Okay. All right. Then it says find India's population to the nearest million in the year 2028 as predicted by the function. So then at this point we want to determine the value of x, and so keep in mind that x is years after 1974. So the first thing is to consider how many years after 1974 is 2028. And so we can figure that out by doing some subtraction. So 2028 minus 1974 is 54 years. So then that's the value that we're going to plug in for x into the function. So we're essentially going to find f of 54. So 574 times 1.026 to the 54th power. And then we can work that out on our calculator. So 2295.46 million people. Alright, so the function allows us to make predictions, which you can obviously understand how important that would be for planning purposes. If you're in a city in India or the country of India, right, you want to be able to plan infrastructure, be able to essentially carry that many people. So you want to have the carrying capacity available to manage this many people. So that would be a good thing for planning purposes. What year will the population reach 4,590 million? So this switches it up. So essentially we're trying to find the year for this particular population. So we want to essentially solve this particular problem. We haven't quite gotten into logarithms yet, which is what you would use to solve an exponential function. So I'm going to do this with our graphing calculator, do that graphically. So let me show you how I'm going to do that. There's a little bit of a glare there. There's better. So I'm going to go to y equals. I've already got the function in. And then I'm going to graph the line just y equals 4,590. And so I'm going to have to zoom out a little bit. And I'm trying to get both of those graphs on here. zoom out even further. Okay. And so the curved line is my exponential function that we started with. This is the line y equals 4,590. So essentially I'm trying to find where those two intersect, or where those two meet is when it is the year in which the population will be 4,590 million. So your calculator will find that point if you do second trace and you go to number 5 intersect and just hit enter, and then it'll ask you for first curve, just hit enter. You're basically saying, yeah, look on that graph, and then second curve, look on the other graph, just hit enter, and then just enter for guess. So basically just hit enter 3 times and it'll tell you that intersection point. And so that intersection point is roughly 81. Okay. So x is equal to 81. Okay. And so then we have to figure out what year that is. So keep in mind here the directions say that x is years after 1974. So then I want to essentially add 81 to 1974. And that should give me the year in which that will occur. And so in 2055, the population would be 4,590 million. All right, that's a lot of people. Okay, so that's an application of exponential growth. Okay. The other type of exponential function we can have is exponential decay. This occurs when a is still positive but between 0 and 1. Okay. So this is an important aspect. And here's what a graph of exponential decay looks like. So this is an example. You can see that you've got data that is decreasing rapidly, right? So you still see that curve, but it's decreasing instead of increasing. This is an example in regards to radioactivity, time in weeks. So think about half-lives of radioactive substances. That's one application of exponential decay that's used quite frequently. Here's another example of exponential decay that we can take a look at. Let's see. So this is depreciation of a vehicle. So if you haven't figured it out already, as soon as you buy a vehicle, it starts to depreciate. Until, sometimes if they become antiques, they could be worth more money than you paid for them, but that takes a while. So notice that this is an exponential decay function because a is between 0 and 1, so it's a decimal. So that's kind of the telltale sign. This number here is once again the initial value. So basically what this function is saying is that the person bought the car for $16,630 and it's basically decreasing at a rate of 10% per year. Okay, that's 100% minus 10% is where the 0.90 comes into play. Okay. And we could graph that. So let me graph this on the calculator real quickly, hopefully. Alright, so I'm going to fit a window here, try to get this to work. So X is years, so I'm just going to do 0 to 10. and then y is the price. So the y min would be 0, and then the max would be 16630, since that's how much they bought the car for. And so that should give us a pretty good window. Let's see what we got. There we go. I tried zoom fit, but I wasn't really getting a good picture. So fitting the window manually here isn't too difficult, but you can see that curve, you know, the exponential decay curve. So it's decreasing at a pretty good clip there. All right. And so to answer the questions here, it says, how much should a 3-year-old Civic sedan cost? Well, we are essentially plugging in 3 into the function. So we could use our calculator to find that. And so after 3 years, the car is worth $12,123.27. Okay. How much is it worth after 9 years? So then we essentially put 9 in that exponential spot. And so the car is worth $6,442.80. And so you could obviously see, you know, for planning purposes, if you were going to buy a used car, right, and if you look up Kelley Blue Book prices or Edmunds, right, they're essentially using models that are similar to this to get used car prices, right? Now there are some other variables that are included in that, you know, whether the car has been in an accident, if it's in good shape, so on and so forth. But yeah, even if the car is in pristine condition, right, there's going to be some depreciation just due to wear and tear. So that's what this model is describing. So there's an application of exponential decay. All right. And then we go in to talk about the number e. So the number e is described by the variable e. So it's kind of weird to say the number e since e is a letter, but e is actually a number, and it is essentially what this expression approaches as n becomes increasingly larger. Okay? You can actually find e on your calculator. So let's zoom out a little bit here. So if you find the ln button, so right below logarithms, so ln, and notice you got an e to the x in blue there, so second ln, and that'll pull up e. And so if you do e to the first power, that's what the number e equals, 2.718281828, and it repeats. So that's what that expression approaches as n gets increasingly larger. That's actually part of a compound interest formula. And so as that part of the compound interest formula becomes compounded more and more and more, it approaches this number. And so we typically use e to represent something that's either compounded continuously or model just constant compounding of an exponential function for something like population, right, where the population doesn't just double every month. You know, it's continually increasing every second. And so I don't know if you guys have ever used the continuous compound formula PERT, but you know, that's the e in that is the same e that we're talking about here. So what you guys need to know is just essentially kind of what e is, and then be able to use it, find it on your calculator for the most part. And so here's an example of an exponential formula using e. So it's in regards to drug medication. Let me zoom in just a little bit again. Okay. So it can be used to find the number of milligrams d of a certain drug that is in the patient's bloodstream H hours after the drug has been administered. How many milligrams will be present after 1 hour, after 6 hours? So then if we want to find out how much of the drug is in the system after 1 hour, we're going to plug in 1 for H. And then really what you guys need to be able to do is to, find E on your calculator, plug that expression in, find the value. So that would be E to the negative 0.4 times 1, which is negative 0.4. So remember how I got the E, so second ln, and then just type in the negative 0.4 for the exponent. So then there would be 3.35 milligrams left in the patient's bloodstream after 1 hour. After 6 hours, I'm plugging in a 6 in for H, and so negative 0.4 times 6 is negative 2.4, so 5e to the negative 2.4, and so you get 0.4535. Okay, and that would be milligrams as well, right? So obviously your body is excreting the drug, as time is increasing, right? And so that is a continual process, right? It's happening real time every second, so that's why we're using E to describe that, right? It's not like your body excretes, 2 milliliters, after 2 hours, and then another 2 milliliters after another 2 hours, right? It's continually doing that process of excreting the drug from your body. So that's why we would use something like E for this particular problem. All right. So that should give you enough information to get started with this particular chapter and section. I would still read it in the text, in the book, and then I will assign homework for you guys to try. If you get stuck on any of them, please email me. I'll write up a solution and email it back to you. All right. Have a great day.